Along the southern coast of the United States, the ocean unfurls in a vast, shimmering expanse, its surface catching the first golden rays of dawn. Beneath these tranquil waves, a hidden world pulses with life, a world governed by the ceaseless rhythm of tides, the intricate dance of currents, and the ever-shifting moods of the weather. Here, the story of lobster harvesting is not just one of biology, but of engineering, environmental science, and the relentless ticking of the clock. In this submerged domain, lobster farming unfolds as a marvel of precision and adaptation. Rows of robust sea cages, engineered to endure the ocean's relentless push and pull, are anchored deep into the sea floor. Each cage is a meticulously designed microhabitat, its mesh walls allowing the flow of nutrient-rich seawater while shielding its inhabitants from predators and the open sea. Within these enclosures, thousands of lobsters progress through their life stages, their growth a testament to the delicate balance of environmental control and natural forces. The environment is in perpetual motion. On serene days, sunlight penetrates the water's surface, illuminating the intricate lattice of the cages and the slow, deliberate movements of the lobsters within. Yet the ocean is never truly at rest. Subtle fluctuations in water temperature, salinity, and dissolved oxygen are tracked by an array of submerged sensors, each transmitting real-time data to monitoring systems. These readings are critical, as even minor deviations can signal shifts in the health of the ecosystem, prompting immediate adjustments to maintain optimal conditions. The infrastructure itself is a feat of marine engineering. Heavy-duty nets, reinforced with interwoven steel cables, form the resilient walls of each cage. Buoyant floats keep the structures upright, while massive anchors embedded in the seabed hold them steadfast against the shifting tides and surging currents. Automated feeding systems, suspended above the cages, dispense precise quantities of nutrient-rich pellets at scheduled intervals, ensuring that each lobster receives the sustenance required for healthy growth. The entire system is a symphony of mechanical reliability and biological necessity. Over the course of many months, the lobsters undergo a remarkable transformation. Their exoskeletons harden, their bodies gain mass, and their coloration deepens as they absorb minerals from the sea. Each lobster represents a unique investment of time, energy, and resources, and collectively they form a living fortune, one that can approach $400,000 in value at the moment of harvest. The cages, now heavy with mature lobsters, become both a symbol of success and a source of mounting risk as the harvest window approaches, yet the ocean's bounty is matched by its unpredictability. Far on the horizon a faint shadow emerges, storm clouds gathering, signaling a dramatic shift in the weather. The air thickens, the wind accelerates, and the once calm sea begins to heave. The threat of a tropical storm looms, and with it the spectre of catastrophic loss. The monitoring systems, ever vigilant, detect the first signs of atmospheric instability, triggering a cascade of automated alerts and contingency protocols. The farm's technological backbone springs into action. Weather radar screens flicker with real-time updates, tracking the storm's trajectory and intensity. Wind speed and wave height sensors relay critical data, each data point feeding into sophisticated models that predict the storm's impact on the farm's infrastructure. Automated systems adjust feeding schedules, reinforce cage moorings, and prepare for the possibility of emergency harvest, all without a single human hand in sight. As the storm draws nearer, the sea cages are battered by mounting waves. The buoys strain against their tethers, the nets flex and shudder with each surge, and the entire system is pushed to its structural limits. The automated monitoring network records every stress point, every fluctuation in current, every spike in salinity, feeding this data into a central control system that continuously recalibrates the farm's defenses. In these critical hours, the process of harvest becomes a true race against time. Specialized vessels equipped with hydraulic lifts and reinforced decks are readied by automated systems to retrieve the heavy cages. Each cage is hoisted from the water, its contents transferred to secure, climate-controlled holding tanks designed to shield the lobsters from the elements and maintain their health until the storm passes. The ocean's fury intensifies. Waves crash against the dock, sending spray high into the air. The cages, once secure, now threaten to break free from their moorings. If the storm arrives before the harvest is complete, the entire crop, months or even years of careful cultivation, could be swept away in a matter of hours, lost to the depths. The stakes are absolute. The sea cages, battered and torn by the relentless wind and waves, may spill their precious cargo into the open ocean where the lobsters vanish into the abyss. The intricate web of equipment, nets, buoys, anchors, can be reduced to twisted wreckage, a testament to the raw power of nature and the fragility of even the most advanced technology. In this high-stakes environment, every second is critical. The ocean, the weather, and the intricate machinery of the farm are locked in a tense, dynamic balance. The outcome, whether it is a triumphant harvest or a devastating loss, will be determined in the next 48 hours as the race against time reaches its dramatic and uncertain climax. The odyssey of a lobster, from the moment of fertilization to its emergence as a juvenile, is a marvel of biological engineering and environmental adaptation. This journey begins with the fertilized egg, a minuscule sphere barely visible to the naked eye, securely attached to the pleopods beneath the female lobster's abdomen. Each egg is encased in a semi-permeable membrane which serves as both a barrier and a conduit, protecting the developing embryo from pathogens and toxins while allowing the exchange of gases and the absorption of water. Within the egg, the embryo is nourished by a yolk sac, a vital reservoir of proteins, lipids, and carbohydrates. This yolk not only sustains the embryo's metabolic needs, but also provides the building blocks for the rapid cell division and differentiation that will soon follow. The earlier stages of development are marked by a series of mitotic divisions, transforming a single fertilized cell into a multicellular blastula and then into a gastrula, as the basic body plan of the lobster begins to emerge. The aquatic environment surrounding the eggs is a critical determinant of survival. Water temperature, typically ranging from 24 to 28 degrees Celsius, acts as a master regulator, dictating the pace of embryonic development. Warmer waters accelerate metabolic processes, hastening the progression from egg to larva, while cooler temperatures slow development, extending the incubation period. Salinity, too, must remain within a narrow range. Even minor fluctuations can disrupt the delicate osmotic balance within the egg, leading to dehydration or swelling, both of which can be fatal. Oxygen is another essential factor. The developing embryos respire through their membranes, relying on a steady supply of dissolved oxygen in the water. Hypoxic conditions, where oxygen levels fall too low, can induce cellular stress, impair organogenesis, and ultimately result in embryonic mortality. The eggs are also acutely sensitive to water quality. Trace amounts of heavy metals, pesticides, or other contaminants can compromise the integrity of the egg membrane, increasing susceptibility to infection and reducing hatching success. Over the course of approximately 60 days, the embryo undergoes a remarkable transformation. The process of organogenesis unfolds as specialized cells give rise to the nervous system, digestive tract, musculature, and the first rudimentary exoskeleton. Appendages begin to bud from the body, and the eyes, initially simple pigment spots, develop into complex structures capable of detecting light and movement. The yolk sac is gradually consumed, fueling the energy-intensive processes of growth and differentiation. As the embryo nears the end of its development, the egg membrane becomes increasingly thin and fragile. Enzymatic activity within the embryo weakens the membrane, preparing it for the moment of hatching. When the time is right, the larva, now known as a philosoma, breaks free, propelled by rhythmic contractions of its developing muscles. The Philosoma larva is a creature of the open water, nearly transparent and exquisitely delicate. Its elongated appendages and flattened body are perfectly adapted for a pelagic existence, allowing it to drift with the currents and evade many would-be predators. At this stage, the larva is entirely dependent on the planktonic ecosystem, feeding on microscopic algae, copepods, and other tiny organisms suspended in the water column. Growth during the larval stage is rapid and punctuated by a series of molts. Each molt involves the shedding of the exoskeleton, a process that allows the larva to increase in size and undergo significant morphological changes. The intervals between molts are governed by environmental factors, especially temperature and food availability. After each molt, the larva is soft and vulnerable, its new exoskeleton taking time to harden and provide protection. With each successive molt, the philosoma becomes more robust. The appendages differentiate further with the development of specialized feeding structures and sensory organs. The digestive system matures, enabling the larva to process a wider range of prey, while the nervous system becomes increasingly complex, allowing for more sophisticated behaviors such as prey capture and predator avoidance. The environment continues to exert a profound influence on the developing larvae. Water temperature not only affects the frequency of molts, but also shapes metabolic rates and energy allocation. Food availability is a constant challenge. The larvae must efficiently locate and capture prey in a vast and often unpredictable ocean. Those that fail to secure enough nutrition are quickly outcompeted or fall victim to starvation. After several molts, the larva enters the post-larval stage, a dramatic metamorphosis that marks the transition from a pelagic to a benthic lifestyle. The body becomes more compact, the claws and walking legs develop, and pigmentation increases, providing essential camouflage against the seafloor. The post-larva now closely resembles a miniature adult lobster, equipped with the anatomical and physiological adaptations necessary for life on the bottom. Instinctively, the post-larval lobster seeks out shelter among rocks, crevices, or seagrass beds, minimizing its exposure to predators. This shift to a benthic existence is a critical survival strategy, as the seafloor offers both protection and access to new food sources, such as detritus, small invertebrates, and organic matter. The journey from egg to juvenile is fraught with peril at every stage. Predation, competition, environmental fluctuations, and physiological stress claim the vast majority of individuals before they ever reach the safety of the benthic zone. Only a tiny fraction of the original cohort survives, each juvenile a testament to the power of adaptation and the relentless pressures of natural selection. Now, as robust juveniles, these lobsters are ready to face the vast, unpredictable expanse of the open sea. Armed with the resilience and adaptations forged during their extraordinary transformation, they embark on the next chapter of their lives, one that will test their survival skills in the ever-changing marine environment. Once the juvenile lobsters reach a robust stage, they are carefully transferred from the safety of the inland hatchery to a meticulously engineered environment in the open ocean, a transition that is both a leap into the wild and a step into a world of precision control. This move is pivotal, as the oceanic home is designed to mimic the natural habitat while providing a level of protection and regulation impossible in the wild. The lobsters are introduced into expansive sea cages, vast underwater enclosures that represent the pinnacle of marine engineering. Each cage, typically spanning 2 square meters, is constructed to endure the relentless push and pull of ocean currents, storms, and tides, ensuring a stable environment regardless of surface conditions. The frames are forged from advanced corrosion-resistant alloys, chosen specifically to withstand years of exposure to salt water without weakening or leaching harmful substances into the ecosystem. Encasing these frames are specialized nets, woven from high-tensile, flexible fibers that resist tearing and biofouling, yet allow for the natural movement of water. These mesh walls are engineered to permit a continuous flow of oxygen-rich seawater, ensuring that the lobsters are bathed in fresh, life-sustaining currents while remaining securely contained. Anchored deep into the seabed, the cages are positioned to maximize exposure to clean, nutrient-laden water while minimizing the risk of sediment accumulation or stagnation. The habitat is a complex, self-contained ecosystem, isolated from the open ocean, yet intimately connected through the constant exchange of water and nutrients. On the surface, anti-wave buoys absorb and dissipate the energy of passing swells, reducing turbulence within the cages and creating a calm, stress-free environment below. Beneath the waves, a sophisticated network of sensors and cameras is integrated directly into the cage infrastructure, forming a digital nervous system that constantly monitors every aspect of the environment. These devices transmit real-time data, providing a continuous stream of information about the physical, chemical, and biological conditions within the enclosure. The system is designed to maintain an optimal microhabitat, even as the surrounding ocean shifts from tranquil to tempestuous. Sensors act as vigilant sentinels, detecting subtle changes in water chemistry and physical conditions that could impact lobster health. They continuously track parameters such as temperature, pH, turbidity, and dissolved oxygen, ensuring that every variable remains within the ideal range for lobster growth. Salinity is monitored with precision, as even minor fluctuations in salt content can affect the lobster's osmoregulation and overall vitality. Oxygen sensors ensure that the water remains saturated with life-giving gas, preventing hypoxic conditions that could threaten the entire population. Current meters measure the speed and direction of water flow, which is critical for delivering nutrients and removing metabolic waste from the enclosure. Any deviation from the established parameters triggers an immediate alert, allowing for rapid intervention to restore balance. This automated vigilance ensures that the lobsters are never exposed to dangerous shifts in their environment, maintaining a delicate equilibrium at all times. The result is a sanctuary where lobsters can thrive, free from the stresses of predation, pollution, and competition that define life in the open sea. The physical barriers of the cage keep out natural predators, while the controlled environment shields the lobsters from harmful algal blooms, parasites, and disease outbreaks. Within this carefully balanced ecosystem, the lobsters have access to optimal nutrition, clean water, and stable conditions supporting rapid growth and robust health. Over time, the lobsters adapt to their secure oceanic home, molting and growing as they would in the wild, but with the added benefit of constant protection and support. Each molt marks a new stage of development, with the lobsters increasing in size and value, all under the watchful presence of advanced monitoring systems. Through this intricate blend of technology, chemistry, and ecology, the controlled oceanic home produces lobsters of exceptional quality, perfectly suited for the demands of the global market. Inside the engineered environment of sea cages, the feeding process for lobsters is a meticulously orchestrated operation designed to support not only survival but also optimal physiological development. Lobsters, as benthic crustaceans, possess a digestive system uniquely adapted to process a wide range of organic matter. Their mandibles and maxillopods manipulate feed particles, which are then broken down by a combination of mechanical action and digestive enzymes secreted in the foregut and hepatopancreas. The efficiency of this process is directly influenced by the physical form, particle size, and nutrient composition of the feed provided. In aquaculture, the feed is engineered to closely replicate the nutritional complexity of a wild lobster's diet. Commercial lobster feed is typically composed of 45 to 55% high-quality protein sourced from fish meal, squid meal, and crustacean byproducts. Lipids, primarily omega-3 and omega-6 fatty acids, are included at 8 to 12% to support membrane integrity and energy storage. Carbohydrates, though less critical, are present in small amounts to facilitate energy metabolism. The feed is extruded into water-stable pellets, ensuring minimal nutrient leaching and maximum palatability. Essential micronutrients are precisely incorporated into the feed matrix. Calcium and phosphorus are critical for exoskeleton calcification, while magnesium, zinc, and copper play vital roles in enzymatic reactions and immune defense. Vitamin C and E are added as antioxidants, protecting tissues from oxidative stress during rapid growth phases. Choline and inositol support lipid transport and cellular signaling, further enhancing growth efficiency. Specific feed additives are included to influence phenotypic traits. Astaxanthin, a carotenoid pigment, is supplemented to intensify shell coloration, a key indicator of health and market value. Betaine and nucleotides are added to improve stress resistance and enhance the immune response, reducing susceptibility to pathogens in the high-density environment of sea cages. The feeding process is governed by advanced monitoring systems. Sensors continuously track water temperature, dissolved oxygen, ammonia, and pH, all of which influence lobster metabolism and feed conversion efficiency. Artificial intelligence algorithms process biometric data such as average lobster weight, molting frequency, and feed intake rates to dynamically adjust feeding schedules and ration sizes. This closed-loop system ensures that each lobster receives the precise quantity and quality of nutrients required for its developmental stage. Juvenile lobsters, with their accelerated metabolic rates, are fed up to 4 times daily, with rations calculated to deliver 15 to 20% of their body weight in feed during peak growth. As lobsters mature, feeding frequency is reduced and ration size is adjusted to prevent overfeeding and optimize feed conversion ratios, which can reach as low as 1.5. 1 in well-managed systems. Overfeeding is rigorously avoided, as uneaten feed can decompose, elevating ammonia and nitrite levels and disrupting the delicate microbial balance within the sea cage ecosystem. Automated feeders are calibrated to dispense feed in small, frequent doses, allowing lobsters to consume all available nutrients before significant leaching or decomposition occurs. This precision minimizes environmental impact and maintains optimal water quality for sustained growth. The efficiency of this feeding protocol is measured by the feed conversion ratio, FCR, a critical metric in aquaculture. A low FCR indicates that lobsters are converting feed into body mass with minimal waste, reflecting both the quality of the feed and the precision of the feeding system. This scientific approach ensures that every gram of feed contributes directly to the future harvest, maximizing both yield and sustainability. The result is a lobster with firm, resilient muscle tissue and a lustrous, well-calcified shell, attributes that are direct outcomes of precise nutritional management. The adage, "you are what you eat," is validated at the molecular level as the composition of the feed is mirrored in the quality of the final product. Through the integration of nutritional science, environmental monitoring, and automated feeding technology, the future harvest is shaped long before the lobsters reach market size. Each stage of growth is supported by a tailored diet, ensuring that the harvest will meet the highest standards of quality, sustainability, and efficiency. The journey from sea cage to harvest is defined by the science of feeding, a process where every detail is engineered for success. The value of a lobster is a moving target, shaped by a complex interplay of market demand, size, and quality. Yet beneath the surface, the journey from ocean floor to market is fraught with relentless, multifaceted pressures. Each lobster harvested is the result of a delicate balance between environmental volatility, biological threats, and logistical obstacles, forces that operate with or without human presence. In the open water, lobster cages are at the mercy of the elements. The sea is a living, shifting force, and storms can materialize with little warning. Towering waves and howling winds churn the surface, sending surges that threaten to rip cages from their anchors. A single tempest can transform a thriving harvest into a field of empty, overturned cages, as the ocean reclaims what was once secured. Even after the storm passes, debris and battered equipment may drift in the harbour, silent evidence of nature's power. The ocean's challenges persist even in moments of calm. Salt water is a relentless adversary, corroding metal hinges, weakening ropes, and eating away at the mesh that forms the cage's only defence. Tides pull and push with unceasing force, while underwater currents batter the cages day and night. Over time, these forces wear down the barriers, creating vulnerabilities that can lead to catastrophic equipment failure. A single rusted hinge or frayed rope can open the way for escape or intrusion, turning a secure trap into a liability. Biological threats lurk in the shadows. Predators such as eels, crabs, and octopuses are adept at infiltrating cages, slipping through gaps to prey on the lobsters within. Larger fish and opportunistic sea creatures may attack from outside, testing the strength of the mesh and the resilience of the structure. The constant pressure from these predators means that every cage is a battleground, its contents under siege from the wild at all times. Invisible dangers are ever present in the form of disease and water quality. A sudden drop in temperature, a shift in salinity, or a decrease in dissolved oxygen can stress or kill lobsters in a matter of hours. Marine pathogens, undetectable to the naked eye, can sweep through a population, leaving devastation in their wake. The underwater environment is a fragile system, and even the smallest imbalance can trigger mass mortality, turning a healthy stock into a scene of loss. The timing of the harvest is a high-stakes calculation. The threat of an approaching storm forces a critical decision: harvest early, accepting smaller and less valuable lobsters, or wait and risk losing everything to the elements. Each cage, loaded with its living cargo, becomes a wager, sometimes worth hundreds of thousands of dollars, against the unpredictable moods of the sea. Every lobster that survives this gauntlet and reaches the shore is a testament to resilience. Its value is not only in its freshness or size, but in its survival through a gauntlet of environmental, biological, and logistical hazards. In the high-stakes world of lobster harvesting, the true contest is not just in the marketplace, but in the ceaseless, unpredictable, and often unforgiving embrace of the ocean itself. When the decision to harvest is made, the vessel begins its critical journey across the open water, its hull slicing through the rolling waves. The boat glides steadily, guided by the rhythm of the sea, moving toward the floating lobster cages anchored far from shore. The ocean's surface shimmers beneath the vessel, reflecting the sky as the boat approaches its destination. On the deck, specialized equipment stands ready for action. Hydraulic winches, powerful cranes, and reinforced platforms are all meticulously engineered for the demanding task of retrieving the heavy, waterlogged cages from the depths. Each component is designed to withstand the relentless salt spray and the constant motion of the sea. The sea cages, now laden with a thriving lobster population, float in the current. Their weight is a testament to months of careful cultivation, as the lobsters have grown and multiplied within the protective mesh, shielded from predators and the harshest elements of the open ocean. The vessel maneuvers with precision, aligning itself so that the crane is positioned directly above the loaded cage. The boat's hull remains steady, stabilized by ballast and the careful design of its structure, allowing the mechanical systems to operate smoothly even as the waves lap against the sides. Heavy-duty cables are lowered from the crane, their hooks locking securely onto the reinforced frame of the cage. The metal glints in the sunlight, and the cables are tested by the weight of the catch below. With a deep mechanical groan, the hydraulic winch tightens, and the great lift begins. The tension in the cables increases as the machinery works in perfect synchrony, drawing the cage upward through the water column. The cage emerges from the sea, droplets cascading from the mesh as it breaks the surface. The structure, heavy and alive, is hoisted steadily upward, water streaming down in rivulets that glisten in the daylight. Suspended above the waves, the cage sways gently in the breeze, its precious cargo exposed to the open air for the first time since being submerged. The ocean below sparkles, and the cage's shadow dances across the water. Inside the cage, the lobsters react instinctively to the sudden transition. Their antennae wave and claws flex as they adjust from the cool, dark sea to the bright, briny air. The change in pressure and light is immediate, and the lobsters cluster together, seeking the comfort of the familiar mesh. Once aboard, the cage is gently set down onto the reinforced deck. The vessel's stabilizers absorb the impact, ensuring the precious cargo remains undisturbed. The next phase begins, containment and care, a process as critical as the harvest itself. Lobsters are transferred from the cage into advanced mobile holding tanks using automated conveyor systems. These systems are designed to minimize handling and stress, gently guiding each lobster into its temporary aquatic refuge. The holding tanks are far more than simple containers. Each is a sophisticated aquatic environment, engineered to replicate the lobster's natural habitat as closely as possible. Robotic arms and automated gates ensure a seamless transition from cage to tank. Each tank is equipped with advanced temperature controls, keeping the water cool and stable. This calms the lobsters and slows their metabolism, preserving their strength and vitality for the journey ahead. Oxygen is continuously infused into the water through specialized aeration systems. Streams of bubbles rise through the tanks, ensuring the lobsters can breathe easily and remain healthy during transit. Filtration systems operate around the clock, maintaining water clarity and quality. Waste is removed efficiently and the environment remains pristine, free from contaminants that could threaten the lobster's well-being. Sophisticated sensors are embedded throughout the tanks, constantly monitoring oxygen levels, temperature and salinity. Real-time data is relayed to onboard systems, ensuring that any deviation from optimal conditions is corrected immediately. In this carefully controlled environment, the lobsters remain vigorous and healthy. Their shells glisten under the clear water, and their value is preserved for the journey to market. Proper containment and environmental control are essential. Any lapse in these systems can quickly affect the quality of the meat, making vigilance and precision paramount at every stage. As the holding tanks are secured on deck, the vessel prepares for a swift return to shore. The horizon darkens as storm clouds gather, adding urgency to the journey. The engines rumble to life, vibrating through the hull. The boat turns toward the distant coastline, its precious cargo now protected within a mobile aquatic sanctuary, every system working in harmony to ensure safe passage. The journey to shore becomes a race against time and the elements. Ocean spray lashes the glass of the tanks as the boat powers through choppy water, every mechanical and natural process working together to keep the lobsters safe and healthy until they reach land. Upon arrival at the shoreline, the lobsters, still alive and highly sensitive to environmental changes, are transferred directly into a rigorously controlled cold chain system. This marks the beginning of a complex preservation journey, where every variable is meticulously managed to maintain the lobster's biological integrity. The cold chain is a seamless, unbroken sequence of refrigerated environments, each calibrated to precise temperatures and humidity levels. This system is engineered to slow the lobster's metabolic rates, reducing their oxygen consumption and minimizing stress-induced biochemical changes that could degrade meat quality. At every stage, the ambient temperature is kept between 0 and 4 degrees Celsius, a range proven to suppress the proliferation of spoilage bacteria and inhibit enzymatic activity that would otherwise accelerate decomposition. Lobsters are placed in chilled, oxygenated seawater tanks where dissolved oxygen levels are carefully monitored to mimic their natural habitat. This reduces lactic acid buildup in their muscles, preserving the delicate texture and flavor of the meat. The facility's air is filtered and circulated to prevent the accumulation of volatile organic compounds, which can cause off-odors and accelerate spoilage. Surfaces are sanitized with food-safe agents to eliminate microbial contamination. The preservation process continues with a multi-stage cleansing bath. Lobsters are immersed in sterile, temperature-matched seawater, which is continuously filtered and UV sterilized to remove particulates, pathogens, and residual waste. This immersion not only removes external impurities, but also helps stabilize the lobster's internal osmotic balance, reducing physiological stress and further extending their viability. The water's salinity is matched to the lobster's native environment, preventing osmotic shock and ensuring that their gills function optimally throughout the holding period. Automated systems then sort the lobsters by size and weight, using non-invasive sensors to minimize handling and prevent shell damage, which could introduce pathogens or accelerate water loss. Segregation by size is not only a market requirement, but also reduces aggressive interactions between lobsters, which can lead to injury and increased mortality. Each lobster is visually and electronically inspected for shell integrity, color, and activity level, key indicators of health and freshness. The sorting process is rapid, ensuring that lobsters spend minimal time outside optimal environmental conditions, thus preserving their physiological state. Some lobsters are selected for live shipment, while others are prepared for immediate processing, each path requiring distinct preservation protocols. For those destined for processing, the next steps are designed to halt all biological activity as quickly as possible, locking in the lobster's peak condition. Some lobsters are exposed to high-pressure steam in sealed chambers, a process that denatures proteins and inactivates spoilage enzymes within seconds. Immediately after steaming, they are transferred to rapid cooling zones, where forced convection and chilled air bring their core temperature down to near freezing, preventing the growth of thermophilic bacteria. Others undergo flash freezing, a process where lobsters are exposed to sub-zero air, or liquid nitrogen, causing ice crystals to form so quickly that cellular structures remain intact. Each lobster is vacuum sealed in high-barrier packaging, which prevents dehydration and oxidation, and then placed in freezers that reach -40 degrees Celsius, conditions that halt all microbial and enzymatic activity. This ultra-low temperature preservation ensures that the lobster's muscle fibers retain their original texture and the flavor compounds remain unaltered, as if the animal was still alive. Throughout the entire process, environmental sensors continuously monitor temperature, humidity, and atmospheric composition, with automated alerts for any deviation from set parameters. Randomized samples are extracted from storage units and subjected to rigorous laboratory analysis. Analytical instruments measure pH, water activity, and muscle firmness, biological markers that indicate freshness and the absence of spoilage. These scientific assessments provide quantifiable assurance that the preservation protocols are functioning as intended. Only lobsters that meet strict biological and environmental criteria are selected for final packaging, ensuring that only the highest quality specimens continue through the supply chain. The packaging itself is engineered for thermal insulation and moisture control, maintaining a stable microclimate around each lobster during transit. Once sealed, the cargo is loaded into refrigerated transport units where temperature and humidity are logged in real time by embedded sensors. For long-distance and international shipments, the lobsters are placed in insulated, temperature-controlled containers, which are then transferred to climate-regulated cargo holds in aircraft. Advanced GPS and environmental monitoring systems provide continuous data streams, allowing for immediate intervention if any parameter drifts from the optimal range. By the time the lobsters reach their destination, the combination of biological, technical, and environmental controls ensures that they remain in a state of peak preservation, virtually indistinguishable from the moment they left the ocean. The final stage of the lobster's journey is a marvel of global logistics, where technology and precision come together to ensure the freshest product reaches its destination. Once processed and packaged, each lobster shipment is sealed in insulated containers and marked with a unique QR code. This digital passport allows for real-time tracking as the package moves through a vast network of shipping routes. Inside every container, advanced temperature sensors are installed. These devices continuously monitor the internal environment, ensuring the cold chain remains unbroken from the moment the lobster leaves the processing facility. If the temperature rises above a critical threshold, automated alerts are triggered and backup cooling systems activate to protect the shipment. For live lobsters, the journey is even more complex. They are packed in specially engineered containers equipped with oxygenation technology and water filtration systems, essentially creating mobile aquariums that maintain optimal conditions throughout transit. From the coastal facility, shipments are swiftly transferred to refrigerated trucks or directly into the temperature-controlled cargo holds of airplanes. These vehicles and aircraft are meticulously maintained to preserve the precise environmental conditions required for the lobster's survival. The global journey spans thousands of miles, with routes carefully planned to minimize transit time. Lobsters may travel from the American coast to major hubs in Asia and Europe, crossing oceans by air or sea, guided by sophisticated logistics software that optimizes every leg of the trip. At each border, automated customs systems scan and clear the shipments, ensuring compliance with international regulations while minimizing delays that could threaten the lobster's freshness. Despite these precautions, any disruption, such as a temperature spike or delay, can compromise the shipment. A single failed container represents a total financial loss, underscoring the high stakes of this global operation. The journey concludes as the lobster arrives at its final destination, often a fine dining restaurant thousands of miles from where it was harvested. Here, the sweet, firm meat is served as a testament to the intricate, technology-driven process that brought it from ocean to table. This global journey, powered by environmental controls, advanced handling procedures, and seamless logistics, is a remarkable example of how technology connects distant oceans to dinner plates around the world. The dramatic harvest of lobsters amid turbulent seas is a striking symbol of the ongoing tension between human ambition and the untamable forces of nature. This delicate balance is at the heart of the lobster industry, where every harvest is a negotiation with the environment and every season brings new challenges. The future of lobster as a delicacy depends on our ability to adapt and innovate within this high-stakes world of aquaculture. Increasingly, technology is transforming how lobsters are farmed and harvested, allowing for more precise control over water quality, feeding, and animal health. As global demand for seafood rises, the pressure to produce more while minimizing environmental impact grows ever more intense. Modern aquaculture facilities are at the forefront of this evolution, using automation and artificial intelligence to optimize every aspect of production. The integration of traditional methods with cutting-edge technology offers a blueprint for sustainable seafood production. These innovations provide a glimpse into a future where lobster farming can be both productive and environmentally responsible. From controlled hatcheries to AI-managed feeding schedules, every step is designed to reduce waste, improve survival rates, and lessen the impact on wild populations. Artificial intelligence and automation are making it possible to monitor lobster health in real time, ensuring a more reliable and sustainable food source. By raising lobsters in contained, carefully managed environments, we can significantly reduce the strain on wild stocks and help preserve marine biodiversity. This approach not only safeguards wild populations from overfishing, but also supports broader conservation efforts. Overfishing remains a significant threat, but sustainable aquaculture offers a viable path forward. The ability to control diet and monitor health at every stage leads to a consistently high-quality product, meeting the expectations of a discerning global market. Quality control, enhanced by technology, ensures that only the best lobsters reach the market, reinforcing the reputation of this prized delicacy. Precision aquaculture, driven by data and innovation, is redefining what it means to farm the ocean responsibly. These advancements mark a significant step toward a future where seafood production is both efficient and ecologically sound. Yet the industry faces ongoing challenges. Climate change brings more frequent and severe storms, threatening the stability of coastal aquaculture operations. The impacts of a warming planet, rising sea levels, ocean acidification, and unpredictable weather demand constant adaptation and resilience. Another concern is the reliance on wild-caught fish for feed, which can undermine the very sustainability aquaculture seeks to achieve. The search for alternative, eco-friendly feed sources is critical to reducing the industry's overall environmental footprint. Developing more resilient farming systems and sustainable feed options will be essential for the long-term viability of lobster as a delicacy. The ultimate goal is to create a system that is not only profitable, but also truly sustainable, one that gives back to the ocean as much as it takes. By working in harmony with the ocean, rather than simply extracting from it, we can ensure the future of lobster for generations to come. The story of lobster farming is ultimately one of adaptation, innovation, and respect for the natural world. It is a world where scientific precision meets the raw power of the sea, and where the future of a delicacy depends on our ability to learn and evolve. In this high-stakes environment, a year's work can be won or lost in a matter of days, underscoring the need for resilience and foresight. As we look ahead, the lessons learned from these innovative coastal farms will shape the future of sustainable seafood worldwide. The future of lobster as a delicacy will be defined by our commitment to sustainability, our embrace of technology, and our respect for the ocean's limits. By learning from the past and investing in the future, we can ensure that lobster remains a symbol of both culinary excellence and environmental stewardship. To truly cultivate the ocean's bounty, we must approach it with intelligence, humility, and a deep understanding of the interconnected world beneath the waves. Only then can we secure a future where lobster continues to be enjoyed as a delicacy, sustainably, responsibly, and in harmony with the sea. The ocean's depths hold both mystery and promise, and the future of lobster will be written by those who respect and protect this remarkable world. Beneath the ceaseless motion of the ocean's surface, a hidden world unfolds, a world where the journey of a lobster is dictated by ancient, unyielding forces. Here, every moment is a contest for survival, shaped by the raw power of nature. From the instant a lobster larva hatches, it is cast adrift into the vast open ocean. The water teems with life, but also with peril. Each larva is a fragile speck surrounded by a swirling mass of plankton, tiny fish, and unseen predators lurking in the blue expanse. These minuscule larvae drift helplessly, carried by unpredictable currents. With no means to defend themselves, they are at the mercy of the ocean's whims, swept into nutrient-rich eddies or stranded in barren waters, their fate determined by the invisible hand of the tides. Danger is ever present. Schools of fish dart through the water, their sharp eyes scanning for movement. Jellyfish drift silently, their tentacles trailing like deadly nets. Even other crustaceans, larger and more aggressive, patrol these waters, turning the early days of a lobster's life into a relentless struggle to avoid becoming a meal. Only a tiny fraction of larvae survive this gauntlet. Those that do eventually settle onto the seabed, where a new set of challenges awaits. Here the young lobsters must quickly find shelter among rocks and seaweed, seeking out crevices that offer protection from the ever-watchful eyes of predators. As juveniles, lobsters become masters of concealment. They wedge themselves deep into rocky cracks, using their spiny bodies to block entry. Their coloration blends with the mottled sea floor, making them nearly invisible to passing hunters. Yet even the best hiding spot offers only temporary safety. The ocean floor is a hunting ground for skilled predators. Octopuses glide silently, their arms probing every crevice. Cod patrol the shadows, their keen senses alert to the faintest vibration. Large crabs scuttle among the rocks, their powerful claws ready to seize any unwary juvenile. Each predator has evolved to exploit the weaknesses of its prey, and the young lobster must remain ever vigilant. Even the lobster's hard shell, a suit of armor grown through painful molts, is not an impenetrable defense. When threatened, a lobster will retreat deep into its shelter, folding its antennae and claws tightly against its body. But the shell is only a temporary refuge. Many predators have learned to pry, crush, or outweight their quarry. Beyond the threat of predators, the environment itself poses constant hazards. Shifting sands can bury hiding places, while sudden changes in salinity or temperature can stress the lobster's delicate physiology. The ocean is a realm of extremes, where survival depends on the ability to adapt to rapid, sometimes violent change. Seasonal storms unleash chaos on the seabed. Powerful currents stir up clouds of sediment, reducing visibility and dislodging rocks that once served as safe havens. Young lobsters are swept from their shelters, forced to navigate a landscape transformed by the fury of the sea. Shifts in water temperature and oxygen levels can disrupt the lobster's growth and development. A sudden drop in oxygen can suffocate both prey and predator, while harmful algal blooms release toxins that poison the food chain, threatening every creature that calls the ocean home. Lobsters are woven into a complex web of life, their fortunes rising and falling with the health of the ecosystem. They compete with other species for food and shelter, and their survival is linked to the delicate balance of the marine environment. When predator populations shift, whether from natural cycles or environmental upheaval, the entire food web can be thrown into chaos. A decline in one species may lead to a surge in another, altering the balance and creating new threats for the lobster at every turn. The arrival of invasive species or the sudden dominance of a single predator can devastate lobster populations, echoing through the ecosystem in unpredictable and often catastrophic ways. Every stage of a lobster's life is a test of resilience. To survive, they must outwit predators, endure environmental extremes, and adapt to a world in constant flux. Their strategies are as varied as the dangers they face: camouflage, speed, strength, and the ability to regenerate lost limbs. Those that endure grow larger and stronger, their shells thickening with each molt. They learn to read the subtle cues of their environment, seeking out new shelters and adapting to the ever-changing rhythms of the sea. In this hidden, untamed world, the fate of each lobster is a story of struggle and adaptation, a testament to the relentless power and unpredictability of nature's gauntlet, where only the most resilient survive. In the shadowy depths of the ocean, where sunlight barely penetrates and the pressure is immense, survival is dictated by a suite of extraordinary adaptations. Here, lobsters have evolved over millions of years, their bodies and behaviors shaped by the relentless demands of their environment. Lobsters possess a robust exoskeleton, or carapace, composed primarily of chitin and reinforced with calcium carbonate. This armor not only shields them from predators, but also provides structural support in the crushing depths. Their segmented bodies and articulated joints allow for remarkable flexibility, enabling them to navigate the complex terrain of rocky crevices and dense seaweed forests. Camouflage is a primary defense. Specialized chromatophores within their shells allow lobsters to subtly alter their coloration and pattern, blending seamlessly with sand, rocks, and seaweed. This adaptive coloration is controlled by hormonal signals and can shift in response to environmental cues, making lobsters nearly invisible to both predators and prey. When growth or injury demands, lobsters undergo molting, a complex physiological process regulated by ecdysteroid hormones. The lobster absorbs water to swell its body, splits its old exoskeleton and wriggles free, exposing a soft, vulnerable new shell beneath. During this period, the lobster is at its most defenseless. The new exoskeleton, initially pliable, gradually hardens as minerals are redeposited. This process can take several days, during which the lobster seeks refuge in secluded crevices, minimizing movement to avoid detection. The act of remaining motionless is a critical survival tactic. By reducing movement, the lobster decreases its chances of being detected by visual or mechanosensory predators, relying on the safety of its chosen shelter until its armor is restored. Lobsters are equipped with two highly specialized claws, or chelae, each serving a distinct function. The crusher claw, broad and powerful, is designed to break shells and crush prey, while the cutter or pincer claw is slender and sharp, ideal for slicing and manipulating food. This dimorphism is genetically determined and develops as the lobster matures. The claws are not only tools for feeding, but also formidable weapons for defense. Lobsters can regenerate lost limbs, a process known as autotomy, which is triggered by neural and hormonal signals following injury. This ability ensures that even after violent encounters, lobsters can recover and maintain their survival edge. When threatened, lobsters employ a rapid escape response known as the caridoid escape reaction. By forcefully contracting their powerful abdominal muscles, they flick their tails and propel themselves backward in a sudden burst, creating a cloud of sand to obscure their retreat. This reflex is mediated by giant interneurons, allowing for split-second reactions to danger. Lobsters' long, sensitive antennae are packed with chemoreceptors and mechanoreceptors, enabling them to detect minute changes in water movement and chemical composition. These sensory organs are crucial for navigation, locating food, and identifying both predators and potential mates in the dark, turbid waters. Their nervous systems are finely tuned for rapid processing of sensory information, granting lobsters exceptional reflexes and the ability to evade threats with remarkable agility. This neural sophistication is a product of evolutionary pressures in a habitat where only the most adaptable survive. Each adaptation, armor, camouflage, regeneration, rapid escape, and acute sensory perception, represents a chapter in the evolutionary saga of the lobster. These traits, honed over eons, ensure that the lobster remains a master of survival in the ever-changing, unforgiving world of the deep sea. Beneath the surface, the ocean's currents move with silent, relentless power, an invisible hand that shapes every moment of a lobster's existence. These currents are not just water in motion. They are complex, dynamic systems driven by the gravitational pull of the moon and sun, the spinning of the earth, and the shifting patterns of wind across the sea. They create underwater rivers, some slow and meandering, others swift and forceful, each with its own temperature, salinity, and chemical signature. For lobsters, these currents sculpt the very world they inhabit. The flow of water determines where rocky outcrops form, where sand accumulates, and where nutrients settle. It is the currents that decide which areas become rich, life-filled habitats and which remain barren stretches of seafloor. From the moment lobster eggs hatch, the tiny larvae are swept up by these moving waters. Suspended in the planktonic soup, they drift for weeks. Carried far from their birthplace, the temperature and chemistry of the currents influence their growth, survival, and even the timing of their transformation into juvenile lobsters. Some larvae are transported to nutrient-rich zones, where food is plentiful. Others may be swept into colder, less hospitable waters, where survival is a daily struggle. As they settle to the bottom and begin their benthic lives, young lobsters must quickly learn to interpret the subtle cues of moving water. Their sensitive antennae detect changes in current speed and direction, helping them find shelter from strong flows and locate areas where food is delivered by the tides. Some currents bring a bounty of dissolved oxygen and nutrients, fueling blooms of plankton and supporting entire food webs. These nutrient-rich flows can transform empty sands into vibrant oases, where algae, invertebrates and fish gather, creating ideal hunting and hiding grounds for lobsters. Yet not all currents are benign. Sudden shifts in water movement can signal the approach of storms, bringing turbulence and danger. Strong flows may sweep in predatory fish or stir up sediments, clouding the water and making it harder for lobsters to find food or avoid threats. Guided by ancient instincts, lobsters respond to these changes with purposeful migrations. In summer, as surface waters warm and oxygen levels shift, they journey to deeper, cooler regions where conditions are more stable. When autumn arrives and the currents change again, they return to shallower grounds, following the chemical and physical cues carried by the water. The boundaries of lobster populations are drawn by the invisible lines of ocean currents. These flows separate groups, shape genetic diversity, and determine where new generations will settle. In some places, swirling eddies create isolated pockets of habitat. In others, broad currents connect distant populations, allowing for the spread of life across vast distances. Rocky reefs, dense kelp forests, and sandy burrows are not chosen at random. Each habitat is a product of the ocean's physical and chemical forces, shaped by the way currents deposit nutrients, sculpt the landscape, and influence the availability of shelter and food. In this ever-moving world, survival depends on a lobster's ability to adapt. Sometimes they must ride the current, letting it carry them to new opportunities. At other times they anchor themselves to rocks or burrow deep into the sand, resisting the pull of the water and waiting for calmer conditions. The story of the lobster is written in the language of the sea, a tale of adaptation, resilience, and the constant interplay between biology and the physical world. Each migration, each journey across the seafloor is a testament to the power of the currents. These invisible forces guide lobsters through a labyrinth of ever-changing conditions, shaping their lives from the moment they hatch to the day they anchor themselves against the tide, season after season, generation after generation. The world's oceans are in the midst of profound transformation. As global temperatures rise, the intricate network of ocean currents, responsible for distributing heat, nutrients, and life itself, begins to shift in unpredictable ways. These currents, once stable, now fluctuate, altering the very environment that lobsters have adapted to over millions of years. Sea temperatures are climbing at an unprecedented rate, especially in the shallow coastal waters where lobsters thrive. This warming not only accelerates lobster metabolism, increasing their need for food, but also disrupts the delicate balance of oxygen and nutrients in the water. Simultaneously, ocean acidification caused by the absorption of excess atmospheric carbon dioxide alters the chemistry of seawater, making it more difficult for marine organisms to maintain their physiological processes. As the thermal boundaries of the ocean shift, lobsters are forced to migrate northward, abandoning ancestral habitats that have become inhospitable. This migration is not merely a change in location, it is a journey into unfamiliar ecosystems, where the rules of survival are rewritten. Juvenile lobsters, once sheltered in the protective embrace of seagrass nurseries, now encounter new predators and altered food webs. Warmer waters can increase the abundance of predatory fish while simultaneously reducing the availability of the small invertebrates and detritus that young lobsters rely on for nourishment. The timing of spawning cycles and migration patterns, finely tuned to seasonal cues over millennia, are thrown into disarray by erratic temperature swings and shifting currents. Lobsters may spawn earlier or later than usual, leading to mismatches between larval release and the availability of planktonic food sources. Ocean acidification, a silent but relentless force, lowers the pH of seawater. This chemical shift interferes with the ability of lobsters to extract calcium carbonate from the water, a critical component for building and maintaining their exoskeletons. For young lobsters, the challenge is especially acute. As they attempt to molt and grow, the weakened availability of calcium carbonate results in thinner, more fragile shells. These shells offer less protection from predators and environmental stresses, increasing mortality rates among juveniles. The stress of a changing environment also weakens immune systems, making lobsters more susceptible to disease. Pathogens and parasites, once kept in check by stable conditions, can now spread more easily, further reducing the number of juveniles that survive to adulthood. The habitats that once provided refuge, rocky reefs and lush kelp forests, are themselves under siege. Rising temperatures and acidification can stunt kelp growth, while invasive species and disease threaten the structural integrity of these underwater forests. Increased storm frequency and intensity driven by a warming climate stir up sediments and strip away vital habitats. The once complex seafloor becomes barren, offering fewer hiding places for lobsters to evade predators. From the earliest stage, as drifting larvae exposed to changing currents and fluctuating temperatures, to adulthood on the ocean floor, every phase of the lobster's life is now shaped by environmental instability. The ancient equilibrium between lobsters and their environment is unraveling. Turbulent waters and shifting ecosystems force these resilient creatures to adapt or perish in a world that is no longer predictable. In this era of rapid climate change, the fate of the lobster is a complex narrative of adaptation, vulnerability, and ecological upheaval. Their future and the future of the ecosystems they inhabit will be determined by the relentless forces of a warming, acidifying, and ever-changing ocean. Beneath the waves, lobsters inhabit a world shaped by intricate communication and complex social structures, all unfolding in the dim, shifting light of the ocean floor. Their lives are orchestrated by a sophisticated language of chemicals, postures, and subtle behaviors honed by millions of years of evolution. In this twilight realm, where visibility is often reduced to mere inches and sound dissipates quickly, lobsters depend on chemoreception, the ability to detect and interpret chemical signals suspended in the water. These cues, carried by the ever-present currents, form the backbone of lobster communication. Lobsters possess highly sensitive antennae and antennules which they flick rhythmically through the water. With each movement they sample the environment, detecting minute traces of molecules left behind by other lobsters. This allows them to identify not only the presence of another individual but also its species, sex, reproductive status, and even its recent diet. When two lobsters cross paths, a silent exchange takes place. Chemical cues reveal detailed information. Whether the other is a potential mate, a rival, or a familiar neighbor, these signals are so precise that lobsters can distinguish between individuals, remembering past encounters and adjusting their behavior accordingly. During the breeding season, female lobsters release powerful pheromones into the water, signaling their readiness to mate. These chemical messages can travel considerable distances, attracting males who detect the scent and follow the gradient to its source. The process is highly selective. Females often choose dominant males, ensuring strong genetic lines. Communication extends far beyond courtship. Lobsters are solitary and fiercely territorial, each staking claim to a shelter, often a rocky crevice or burrow. To defend these territories, lobsters engage in ritualized displays, raising their claws, arching their bodies, and releasing bursts of urine laced with chemical signals. These displays serve as both a warning and a declaration of status. Males, in particular, are known for their aggressive defense of prime shelters. The quality of a shelter can determine access to food, safety from predators, and opportunities for mating, making these territories highly coveted. When a rival approaches, lobsters escalate their displays. They may engage in antennal fencing, where they whip their antennae at each other, or perform push-ups to appear larger. If neither individual yields, the confrontation may intensify, but often the exchange of chemical and visual signals is enough to resolve the dispute without physical harm. In rare cases, a physical clash occurs, with lobsters locking claws in a brief but intense struggle. However, these encounters are usually short-lived, as the risk of injury is high. Most disputes are settled through ritualized posturing, with the loser retreating and the victor reinforcing its dominance through lingering chemical markers. Despite their solitary nature, lobsters form loose social hierarchies, especially in areas with abundant shelters. Dominant individuals occupy the best crevices, while subordinates are relegated to less desirable locations. These hierarchies are dynamic, shifting as individuals grow, molt, or are displaced by stronger rivals. Dominant lobsters enjoy priority access to food and mates, while subordinates must wait for opportunities or risk venturing into open water where they are more vulnerable to predators. The memory of past interactions, encoded in chemical trails, helps maintain order within these hidden societies. After a confrontation, chemical signatures persist in the water, serving as reminders of recent victories or defeats. These lingering cues influence future encounters, allowing lobsters to avoid unnecessary conflicts and recognize established hierarchies. Through this silent, chemical-based language, lobsters navigate a world of competition and cooperation. They forge alliances, avoid rivals, and even share space when resources are plentiful, all without a single sound. In the ever-shifting dance of currents and chemistry, every lobster's story is written in invisible trails and ritualized gestures. The reef becomes a living stage where each interaction shapes the social fabric of the underwater world, and every lobster plays its part in the ongoing conversation of the sea. In the dim realm of the ocean floor, lobsters rely on an intricate array of sensory systems, finely tuned for survival in a world where light is scarce and danger is ever present. Their journey through the deep begins with chemoreception, the ability to detect chemical signals in the water. Specialized antennules, equipped with thousands of sensory hairs called esthetasks, allow lobsters to sample their environment with remarkable precision. As these antennules flick rhythmically, they capture minute traces of molecules, signals from prey, predators, or potential mates, enabling lobsters to interpret a chemical map invisible to the human eye. Beyond chemoreception, lobsters possess highly developed mechanoreception. Tiny sensory hairs, or setae, cover their bodies and appendages, detecting the faintest vibrations and water movements. This system alerts lobsters to the approach of other animals, the shifting of sediment, or the flow of currents, allowing them to respond instantly to changes in their surroundings. Their long antennae act as tactile probes, navigating crevices and sensing obstacles in the murky depths. Though often shrouded in darkness, vision still plays a role in the lobster's world. Their compound eyes, perched atop movable stalks, are adapted to low-light conditions. Each eye contains thousands of ommatidia, individual visual units, that collectively form a mosaic image. These eyes are particularly sensitive to movement and contrast, helping lobsters detect predators or prey against the shifting patterns of the seafloor. Unique among crustaceans, lobster eyes use a reflective structure called a tapetum to amplify available light, granting them a distinct advantage in the perpetual twilight of the ocean. Together, these sensory systems, chemoreception, mechanoreception, and vision, create a comprehensive toolkit for navigation and survival. By integrating chemical cues, physical vibrations, and fleeting images, lobsters build a complex understanding of their environment. Every flick of an antennule, every brush of a setter, and every glimmer caught by a compound eye guides their movements through the labyrinthine world below the waves. In this silent, shadowed realm, the lobster's senses are its map, compass, and lifeline. Beneath the waves, the lobster occupies a pivotal niche within the complex tapestry of the marine food web. As both predator and prey, its daily life is a delicate balance of hunting and being hunted. Armed with powerful claws, lobsters are formidable hunters, using their crushing pincers to break open the armored shells of clams, mussels, and sea urchins. Their nimble legs and sharp mandibles make short work of smaller crustaceans, worms, and even fish that stray too close. Opportunistic by nature, lobsters also scavenge on dead animals, recycling nutrients and helping to keep the ocean floor clean. But survival comes with constant risk. The lobster's hard exoskeleton offers some protection, yet it remains a favored meal for a range of marine predators. Large fish such as cod, haddock, and flounder patrol the seafloor, searching for an exposed lobster. Octopuses, with their flexible arms and clever hunting strategies, can reach into crevices where lobsters hide. Even other lobsters may turn cannibal, preying on the vulnerable during molting. Juvenile lobsters face a gauntlet of threats from the moment they hatch. Crabs, seabirds, and bottom-dwelling fish consume countless larvae and young, ensuring that only the most vigilant and lucky survive to adulthood. Yet as adults, lobsters also play a crucial role in shaping their ecosystem. By controlling populations of shellfish and other invertebrates, they help maintain balance on the ocean floor. Their presence influences the distribution and behavior of other species, weaving them tightly into the fabric of the underwater community. In this ever-shifting arena, the lobster is both hunter and hunted, a vital link in the chain of life that sustains the ocean's remarkable diversity. Hidden from sight, yet essential to life, the microbiome of lobsters forms a microscopic world teeming with bacteria, fungi, and other microorganisms. This invisible community resides on the lobster's shell, within its digestive tract, and even in its gills, each habitat supporting a unique array of microbial life. Far from being mere passengers, these microbes play a pivotal role in the lobster's health and survival. Beneficial bacteria aid in breaking down complex food particles, unlocking nutrients that would otherwise remain inaccessible. Some microbes produce enzymes that help the lobster digest tough shells and plant matter, while others synthesize vitamins crucial for growth and molting. The microbiome also acts as a frontline defense. By outcompeting harmful pathogens, beneficial microbes reduce the risk of disease and infection. They help modulate the lobster's immune system, priming it to respond swiftly to threats from the environment. Environmental factors, from water temperature and salinity to diet and pollution, can shift the delicate balance of these microbial communities. Disruptions may leave lobsters more vulnerable to illness or hinder their development, highlighting the microbiome's role as a barometer of overall health. Beyond the individual, the lobster's microbiome influences the broader marine ecosystem. Microbes cycling nutrients within the lobster's gut contribute to the health of the ocean floor, aiding in the breakdown of organic matter and supporting other life forms. In this intricate symbiosis, the lobster and its microbial partners exemplify nature's interconnectedness, where survival depends not only on strength and adaptation, but also on the invisible allies within. For a lobster, growth is impossible without shedding its armor. This process, called molting, is one of the most vulnerable and transformative moments in a lobster's life. It begins with a subtle signal within, the release of hormones that trigger separation between the old shell and the underlying new one. Over days or even weeks, the lobster absorbs calcium from its exoskeleton, softening it and storing the minerals for later use. A thin, flexible new shell starts to form beneath the old, while the lobster swells with water, building pressure. Then the moment arrives. The lobster flexes and contorts, splitting its old shell along the back. With slow, deliberate effort, it pulls itself free. First the body, then the delicate legs and claws. This escape can take several hours and demands precise coordination. Any misstep can prove fatal. Freshly emerged, the lobster is soft and defenseless. It hides, breathing rapidly as seawater rushes in, expanding its new shell to its full size. Over the next few days, stored calcium is redeposited, hardening the new armor. Only then does the lobster venture out, ready to resume its place in the ecosystem. Molting is perilous. Predators are quick to seize the opportunity, and the risk of infection is high while the shell is soft. Yet this cycle of shedding and renewal is essential, not just for growth but for repairing injuries and regenerating lost limbs. Through this risky transformation, lobsters reveal the remarkable adaptations that have allowed them to thrive for millions of years. Beneath the waves, the chemistry of the ocean shapes every moment of a lobster's life. Seawater is more than just a habitat. It is a complex solution, its pH, salinity, and chemical composition directly influencing lobster physiology and survival. Lobsters rely on a stable pH to regulate essential bodily functions. When ocean waters become more acidic, often due to increased carbon dioxide, this delicate balance is disrupted. Acidification weakens lobster shells by hindering their ability to absorb and deposit calcium carbonate, making them more vulnerable to predators and disease. Even slight changes in pH can impair their immune responses and slow growth, especially in early life stages. Salinity, the concentration of dissolved salts, is equally crucial. Lobsters have evolved to thrive within a narrow salinity range. Fluctuations caused by heavy rainfall, freshwater runoff, or melting ice can stress their internal systems. Too little salt and lobsters struggle to maintain cellular balance, risking dehydration and metabolic failure. Pollutants add another layer of complexity. Heavy metals, pesticides, and microplastics can accumulate in lobster tissues, interfering with nerve function, reproduction, and even molting cycles. These contaminants may not always be visible, but their impact is profound, threatening both individual lobsters and entire populations. As the chemistry of the oceans continues to shift, lobsters must adapt to survive. Their health is a silent reflection of the underwater world's changing nature, a reminder that every drop of seawater carries the story of the seas. Hidden within every lobster is a genetic blueprint shaped by millions of years of evolution. The story of lobsters begins deep in prehistory, when ancient ancestors first adapted to life in the world's oceans. Over time, these early crustaceans diversified, giving rise to the modern lobsters we recognize today. At the heart of lobster adaptation lies genetic diversity. Each lobster carries a unique combination of genes that govern everything from shell color and claw size to growth rate and resistance to disease. This diversity is not just a product of random mutation, but also of natural selection. Only those lobsters best suited to their environment survive to pass their genes on to the next generation. Speciation, the process by which new lobster species arise, is driven by changes in habitat, ocean currents, and even subtle shifts in water temperature and chemistry. Isolated populations gradually accumulate genetic differences, eventually becoming distinct species. Today, the world's oceans are home to an array of lobster species, each with traits finely tuned to their ecological niche. Modern genetic research has revealed surprising complexity within lobster populations. Some genes help lobsters withstand warmer temperatures or resist pathogens, while others may enhance reproductive success or influence the timing of molting cycles. These genetic traits, passed down through generations, form the foundation of lobster resilience. As oceans change, the genetic toolkit of lobsters will determine their ability to adapt and thrive. The ongoing story of lobster evolution is written not just in their shells and claws, but deep within their DNA, a testament to the power of life to endure and transform beneath the waves. Beneath the rolling tides, lobsters do not live in isolation. Their world is woven with intricate symbiotic relationships, connections with other marine organisms that can shape their survival and success. Some of these relationships are commensal, where one species benefits while the other remains unaffected. Tiny shrimp and small fish often find shelter within the rocky crevices of a lobster's den, enjoying protection from predators, while the lobster goes about its business, undisturbed. Other partnerships are mutualistic, offering advantages to both parties. Certain species of cleaner shrimp, for example, set up shop at the entrances of lobster burrows. In a delicate dance, these shrimp pick parasites and dead skin from the lobster's shell and gills, gaining a meal while keeping their armored host healthy and free of infection. Even the very substrate of the ocean floor plays a role. Burrowing worms and small crustaceans help maintain the structure of the lobster's home, aerating the sediment and reducing the buildup of harmful bacteria. In return, they benefit from the scraps of food left behind by the lobster's feasts. These subtle alliances reveal a hidden network of cooperation beneath the waves. Each interaction, whether fleeting or long-term, contributes to the delicate balance of the ecosystem. For the lobster, survival is not just a solitary struggle, it is a story of connection, with countless creatures sharing the shelter, nourishment, and protection of the ocean's intricate web of life. After hatching, lobster larvae embark on an extraordinary journey that will determine their fate. Suspended near the ocean's surface, these fragile drifters are at the mercy of powerful ocean currents. The direction, speed, and variability of these currents play a decisive role in where lobster larvae travel and whether they survive. As the tides shift and seasonal winds drive the movement of water masses, larvae can be swept hundreds of kilometers from their birthplace. Some currents act as highways, carrying larvae toward nutrient-rich coastal areas where food is abundant and the chances of survival increase. Others may push them into open waters, far from suitable habitats, reducing their likelihood of settling and maturing. Temperature gradients, salinity, and even the shape of the coastline further influence these dispersal patterns. In certain regions, eddies and gyres create retention zones, natural nurseries where larvae are concentrated and given a better shot at finding shelter and food. Conversely, strong offshore flows can disperse larvae too widely, thinning out populations and making recruitment unpredictable. This delicate balance between drifting and settling is vital for the replenishment of lobster populations. The invisible hand of ocean currents not only shapes the genetic diversity and distribution of lobsters, but also determines the resilience of entire fisheries. In this vast underwater world, the journey of a single larva is a testament to the profound influence of the ocean's ever-moving currents. Beneath the ocean's surface, the lobster's shell stands as a marvel of natural engineering. Known scientifically as the exoskeleton, this rigid outer structure is composed primarily of chitin, a tough, flexible polysaccharide, reinforced with proteins and minerals like calcium carbonate. Together, these elements create a lightweight, yet formidable armor that both protects and supports the lobster's delicate internal organs. The shell serves as the first and most vital line of defense against predators, acting as a physical barrier that resists crushing, piercing, and abrasion. Its layered structure is specially adapted to absorb impacts and distribute force, minimizing the risk of injury. Tiny spines and ridges further deter would-be attackers, while the shell's coloration provides camouflage, blending seamlessly with the rocky seafloor. Beyond protection, the exoskeleton plays a crucial role in locomotion and growth. It anchors powerful muscles that allow the lobster to scuttle, burrow, and wield its iconic claws with precision. However, this rigid casing cannot expand. Instead, lobsters must periodically shed their shells in a process called molting, a vulnerable transformation that allows for growth but leaves them temporarily exposed until a new, larger shell hardens. Additionally, the shell's semi-permeable layers help regulate water balance and exchange vital minerals with the surrounding environment. Specialized glands secrete compounds that strengthen and repair the exoskeleton, ensuring it remains an effective shield throughout the lobster's life. In every facet, the lobster's shell exemplifies the intricate balance of strength, flexibility, and adaptability, a testament to millions of years of evolutionary refinement in the ocean's relentless arena. In the darkest reaches of the ocean, far below the sunlit shallows, a hidden world of deep-sea lobster species thrives. Unlike their coastal relatives, these lobsters inhabit extreme depths, sometimes over 1,000 meters beneath the waves, where pressure is immense, temperatures are near freezing, and light is almost non-existent. Adaptation is the key to their survival. Deep-sea lobsters, such as those in the genus Polycheles, have evolved elongated antennae and specialized sensory organs, enabling them to detect faint vibrations and chemical cues in the pitch-black environment. Their bodies are often softer and more flexible than shallow water species, reducing the risk of injury under crushing pressures. Coloration tends towards pale, translucent, or even red hues, an evolutionary response to the absence of light and the need for camouflage from the many predators that lurk in the gloom. Some species possess bioluminescent patches, possibly used for communication or confusing would-be attackers. The habitat of these lobsters is as remarkable as their physiology. They dwell among hydrothermal vents, cold seeps, and deep continental slopes, where organic matter drifts down from above, sustaining a unique food web. Here, deep-sea lobsters play a crucial ecological role as scavengers and predators, recycling nutrients and maintaining balance in these fragile ecosystems. Their life cycles are adapted to the slow pace of the deep sea, with extended larval phases and slower growth rates. Many species reproduce less frequently, with fewer offspring, ensuring their young are better equipped to survive the harsh conditions. Despite their isolation, deep-sea lobsters are not immune to human impact. Deep-sea trawling, mining, and climate change threaten these ancient survivors, making them a vital focus for ongoing scientific study and conservation. In every way, these extraordinary crustaceans exemplify life's ability to endure and adapt, even in the ocean's most inhospitable depths.